On December 22, 1974, 9 men report for their shift at the Continental Grain Company's massive elevator complex in Westwego, Illinois at mid-afternoon. All 9 lie dead, their bodies scattered across 3 city blocks of twisted steel and burning grain dust. 9 families receive visits from company officials that evening. 9 chairs sit empty at Christmas dinner 3 days later. The explosion tears through the facility with the force of 2 tons of TNT, yet the devastation begins with something as simple as dust particles suspended in air and a bearing that runs just 15 degrees too hot. If you want to understand how this tragedy claimed so many lives in a catastrophic chain reaction that changed industrial safety forever, subscribe to this channel. This episode is a fictionalized reconstruction inspired by real grain elevator accidents and industrial safety investigations. Names, locations, and specific events have been created for storytelling purposes. The Continental Grain Company elevator towers over the flat Illinois landscape like a concrete cathedral, its cylindrical silos reaching 120 feet into the winter sky. On this December morning, temperatures hovered just above freezing, and a thin layer of frost coats the metal catwalks that connect the facility's 23 storage bins. The complex sprawls across 12 acres of former marshland, connected to the Mississippi River by a series of rail lines that bring millions of bushels of corn, wheat, and soybeans through the facility each harvest season. The air inside the working areas carries the sweet, dusty smell of grain, a scent so pervasive that workers joke they can taste it in their coffee during breaks. The facility operates around the clock during peak season, the constant hum of conveyor belts and bucket elevators creating a mechanical symphony that becomes white noise to those who work here day after day. Westwego exists because of grain. The town of 4,200 residents depends almost entirely on the agricultural processing industry that transforms the Midwest's harvest into exportable commodities. 3 major grain elevators operate within the city limits, employing nearly 600 workers between them. The Continental facility alone processes approximately 40 million bushels annually, making it one of the largest operations in the central United States. The complex consists of multiple structures: the head house where grain arrives and begins its journey through the system, the towering concrete silos where millions of pounds are stored in climate-controlled darkness, the shipping building where grain loads onto barges and rail cars, and the maintenance shops where the endless mechanical systems receive attention. Metal dust collection systems snake along the exterior walls, designed to capture the fine particles that grain releases during handling. The December air carries the distant sound of river traffic, tugboat horns echoing across the water as vessels navigate the busy commercial waterway. The facility sits in a region where winter weather can shift rapidly. Today starts clear and cold, but forecasters predict warming temperatures by afternoon, the kind of temperature swing that creates static electricity in dry environments. The grain industry in 1974 operates under safety regulations that focus primarily on fire prevention rather than explosion mitigation. Dust collection systems exist, but their effectiveness varies widely depending on maintenance schedules and operational pressures. The Continental facility has a mixed safety record, neither exceptional nor particularly troubling by the standards of the era. Workers understand that grain dust presents hazards, but the industry has not yet fully grasped the explosive potential of fine organic particles suspended in confined spaces. The prevailing attitude treats dust as a housekeeping issue rather than a catastrophic risk. The Continental Grain Company opened this particular facility in 1958, expanding it twice over the following decade as agricultural production increased throughout the Midwest. The original structure consisted of 12 concrete silos, each capable of holding 150,000 bushels. The 1965 expansion added 11 more silos and upgraded the mechanical systems to handle increased throughput. The facility's bucket elevator system, the vertical conveyor that lifts grain from ground level to the top of the silos, operates continuously during receiving season, moving thousands of bushels per hour through a series of metal buckets attached to a reinforced belt. The system's motor generates significant heat during operation, and the bearings that support the rotating machinery require regular lubrication and monitoring to prevent dangerous temperature increases. Previous incidents at grain facilities across the country provide warning signs that the industry largely ignores. In 1970, a grain elevator in Louisiana experiences a dust explosion that kills 3 workers, but investigators attribute the blast to welding sparks rather than examining systemic risks in grain handling operations. A 1972 incident in Kansas results in 2 deaths when a silo collapses during unloading, but again, the focus remains on structural integrity rather than explosion prevention. The grain industry in this era operates under the assumption that proper housekeeping and spark prevention constitute adequate safety measures. The concept of dust as fuel in an explosive mixture remains poorly understood outside of academic research circles. Insurance companies occasionally flag facilities for excessive dust accumulation, but enforcement remains inconsistent and penalties minimal. Continental's Westwego facility undergoes its last comprehensive safety inspection in September 1974, 3 months before the fatal incident. Inspectors note dust accumulation in several areas, but classify the findings as minor housekeeping issues requiring attention within 90 days. The facility's dust collection system functions, but not optimally. Filters require replacement more frequently than maintenance schedules allow, and some collection points experience reduced suction due to clogged ductwork. The maintenance department operates with a crew of 8, responsible for keeping hundreds of motors, bearings, belts, and mechanical systems functioning across the sprawling complex. Preventive maintenance competes with reactive repairs, and during the busy harvest season that runs from September through December, equipment often runs until it fails rather than receiving scheduled service. The economic pressures of 1974 create additional challenges. Global grain markets experience significant volatility as international demand increases and weather patterns affect crop yields. Continental faces pressure to maximize throughput during the harvest window, pushing equipment and workers to maintain high operational tempo. Overtime becomes standard, and maintenance windows shrink as management prioritizes production over system downtime. The facility operates 6 days per week, with Sundays reserved for essential maintenance only. Workers adapt to the demanding pace, understanding that their livelihoods depend on the facility's productivity and profitability. The men who report for duty on December 22nd represent a cross-section of the local workforce. Shift supervisor Robert Mendoza, 43 years old, has worked at Continental for 18 years, starting as a general laborer and working his way into management. Mendoza knows every system in the facility, having participated in the 1965 expansion as part of the installation crew. Lead operator James Hartwell, 36, operates the main control panel that monitors grain flow through the complex network of conveyors and elevators. Hartwell transferred from Continental's Kansas facility 2 years earlier, bringing expertise in high-volume operations. Maintenance technician Paul Chun, 51, specializes in the mechanical systems, particularly the critical bucket elevator that serves as the facility's primary vertical transport, but Chin's reputation for diagnosing problems quickly makes him invaluable during the busy season. Equipment operators David Santos, 29, and Michael Foster, 34, work the ground-level receiving stations where grain trucks dump their loads into the system. Their job requires constant attention to flow rates and equipment status, watching for jams or mechanical issues that could disrupt operations. Warehouse workers Thomas Riley, 22, Raymond Burke, 47, and Kevin Walsh, 38, handle the physical labor of the facility, cleaning work areas, assisting with equipment moves, and performing general maintenance tasks. Electrician Anthony Russo, 44, rounds out the day shift crew, responsible for the facility's extensive electrical systems that power everything from the massive motors to the control room instrumentation. These 9 men arrive for their shift knowing they face a busy day. The facility holds near-capacity inventory, with 21 of the 23 silos filled to at least 80%. A shipment of 80,000 bushels of corn sits scheduled for transfer to river barges by end of day, requiring the crew to run the bucket elevator system continuously for several hours. The day begins normally, with Mendoza conducting the standard safety briefing at 7 in the morning, reviewing the day's production schedule and equipment status. Hartwell notes in the shift log that all systems show green status, with no outstanding maintenance issues requiring immediate attention. The crew disperses to their stations, beginning the routine that they have performed hundreds of times before. The bucket elevator system at Continental's Westwego facility consists of a continuous belt studded with metal buckets that travel up a vertical shaft enclosed in steel housing. The belt runs over pulleys at the top and bottom of the 120-foot tower, driven by a 100-horsepower electric motor that operates continuously during grain transfer operations. The system moves approximately 10,000 bushels per hour at full capacity, with grain entering at ground level and discharging at the top into a distribution system that directs flow to the appropriate storage silos. The elevator shaft accumulates dust despite the collection system's efforts, as fine particles inevitably escape during the violent motion of grain being lifted and dumped. The dust settles on horizontal surfaces inside the shaft, on the belt itself, and on the structural members that support the system. By 10 in the morning, the crew has the bucket elevator running at full capacity, transferring corn from ground storage to the shipping building's surge bins. The motor hums steadily, its bearings generating heat as they support the massive rotating load. Temperature monitoring for the system consists of a single gauge in the control room that displays bearing temperature, but the gauge provides only a general reading and offers no alarm function if temperatures exceed safe parameters. Chun checks the bearing temperature during his morning rounds, noting that it reads 165 degrees Fahrenheit, within the normal operating range but toward the higher end. He makes a mental note to check it again before lunch, but the facility's busy pace pulls his attention to other systems requiring immediate attention. The bearing that supports the elevator's upper pulley contains grease that lubricates the metal surfaces as they rotate under tremendous load. The bearing received its last service during the September maintenance window, 3 months earlier. The grease gradually breaks down under heat and mechanical stress, losing its lubricating properties and allowing increased friction between metal surfaces. As friction increases, the bearing generates more heat, which further degrades the remaining lubricant in a self-reinforcing cycle. The bearing housing, designed to contain the grease and protect the bearing from contamination, begins to leak as seals deteriorate from heat exposure. Small amounts of hot grease seep out, coming into contact with dust that has accumulated on nearby surfaces. At 11:15, Hartwell notices that the bearing temperature gauge in the control room now reads 185 degrees, a 20-degree increase in just over an hour. He radios Chun to investigate, and the maintenance technician climbs the 120 feet of steel stairs to reach the elevator's head house at the top of the structure. The space at the top is cramped, filled with the machinery that drives the bucket system and the distribution conveyors that direct grain flow. The noise level makes conversation impossible without shouting. Chun approaches the bearing assembly and immediately smells hot metal and degraded grease, a sharp, acrid odor that experienced maintenance personnel recognize as a warning sign. He places his hand near the bearing housing and feels intense heat radiating from the metal surface. The bearing is failing, running far hotter than safe operating temperatures, but shutting down the elevator means halting the day's shipping schedule and potentially missing the barge loading window. Chun faces a decision that maintenance personnel confront regularly in industrial settings: address a developing problem immediately at the cost of production delays, or monitor the situation and plan for repair during the next scheduled downtime. The bearing shows signs of distress, but has not yet failed completely. The system continues to operate, the belt continues to move, and grain continues to flow. Chun decides to increase monitoring frequency, planning to check the bearing every 30 minutes and shut down if conditions worsen significantly. He radios Hartwell with his assessment, recommending that they complete the current transfer operation and then take the elevator offline for bearing replacement. Hartwell agrees, noting the recommendation in the shift log. The decision reflects standard practice in an industry that balances safety concerns against operational demands, but it sets in motion a chain of events that will prove fatal within hours. The bearing continues to deteriorate as the bucket elevator runs. By noon, internal temperatures in the bearing assembly exceed 300 degrees Fahrenheit, hot enough to ignite certain materials under the right conditions. The leaked grease on external surfaces begins to smoke, producing thin wisps that mix with the dust-laden air inside the head house. The bearing's increased friction creates vibration in the system, causing additional dust to shake loose from accumulated deposits throughout the elevator shaft. The concentration of suspended dust particles in the confined space gradually increases, approaching the threshold where organic dust particles can support combustion if ignited. The dust particles, each measuring less than 420 microns in diameter, remain suspended in the air, creating an invisible hazard that none of the workers can detect without specialized monitoring equipment that the facility does not possess. At 12:30, the crew breaks for lunch in the facility's break room, located in a separate building 200 feet from the elevator tower. Mendoza, Hartwell, and several others discuss the bearing issue, with Chen explaining that he plans to shut down the elevator at 2 o'clock to begin the replacement procedure. The conversation remains routine, the kind of operational discussion that occurs daily in industrial facilities. The men eat their lunches, joke about the upcoming Christmas holiday, and make plans for the weekend. Riley, the youngest crew member, talks about his upcoming wedding in February. Burke shows photos of his new grandchild. These ordinary moments represent the last normal interaction these men will have, the final minutes before their workplace transforms into a scene of catastrophic destruction. At 1 o'clock, the crew returns to their stations. The bucket elevator continues to run, now 7 hours into continuous operation. The bearing temperature gauge in the control room reads 210 degrees, a clear indication that conditions are worsening. Chun climbs to the head house once more, bringing tools and a replacement bearing assembly, planning to begin the shutdown procedure and start the repair work. He reaches the top of the stairs at 1:15 and opens the door to the head house. The heat hits him immediately, far more intense than during his morning inspection. The bearing housing glows dull red, visible even in the bright overhead lighting. Chen realizes that the situation has progressed beyond his earlier assessment and reaches for his radio to order an immediate shutdown. The bearing fails catastrophically at 1:17. The rotating shaft, no longer supported by functional bearings, drops slightly and begins to wobble. The metal-on-metal contact generates a shower of sparks as hardened steel grinds against the bearing housing. The sparks, each burning at temperatures exceeding 2,500 degrees Fahrenheit, spray into the dust-laden atmosphere of the head house. The suspended dust particles, primarily composed of cornstarch and protein, constitute an explosive mixture awaiting only an ignition source. The sparks provide that source, and the laws of physics take over with terrible inevitability. The initial deflagration occurs in less than 1/10 of a second. The dust particles nearest to the sparks ignite first, their combustion releasing energy that heats adjacent particles to their ignition temperature. The flame front propagates through the suspended dust cloud at speeds approaching 1,500 feet per second, generating pressure that rises from normal atmospheric pressure to over 100 pounds per square inch in milliseconds. The explosion's force radiates outward from the head house, but the confined space of the elevator shaft creates a chimney effect that channels much of the energy downward through the structure. The pressure wave tears through the steel housing, rupturing seams and blowing out access panels. The sound registers as a sharp crack followed by a deep, rolling boom that echoes across the facility and into the surrounding neighborhood. Chun, standing just 15 feet from the initial ignition point, is caught in the blast's epicenter and does not survive the initial explosion. The pressure wave and thermal pulse prove immediately fatal, and he passes away before he can process what is happening. The explosion blows out the head house walls, sending structural debris in all directions. Large sections of steel housing tear free and become projectiles, some traveling hundreds of feet before impacting the ground or other structures. The initial blast is devastating, but it triggers something far worse. The explosion in the head house disturbs dust deposits throughout the facility, shaking loose accumulated layers from beams, rafters, and equipment surfaces. This newly suspended dust creates additional explosive atmospheres in multiple locations. The pressure wave from the first explosion travels through the facility's interconnected structures, carrying flame and heat into areas where dust concentrations have reached critical levels. Secondary explosions begin to detonate in rapid succession, each one adding to the destruction and triggering additional blasts in a cascading chain reaction that tears through the complex. The second major explosion occurs in the distribution gallery, the enclosed conveyor system that runs from the elevator head house to the storage silos. Hartwell is in the control room directly below this gallery when the blast strikes. The floor above him disintegrates, and the structure collapses. Hartwell and Mendoza, who has come to the control room to coordinate the planned elevator shutdown, are caught in the structural failure and do not survive. The control room, once the facility's nerve center, becomes a tomb of twisted metal and collapsed concrete. The third explosion detonates in the main storage building, where dust has accumulated in the spaces between silos and along the overhead conveyor runs. Santos and Foster are on the ground floor when the blast occurs above them. The explosion's pressure wave travels downward, and the two operators are overcome by the force and falling debris. They pass away within moments, unable to reach safety as tons of structural material collapse around them. The fourth explosion occurs in the shipping building, where Riley, Burke, and Walsh are preparing the surge bins for the afternoon's barge loading operation. The blast originates in the dust collection system, which has accumulated thick layers of fine particles in its ductwork. The explosion propagates through the connected spaces, and the three workers are caught in the confined area with no escape route. They succumb to the blast effects and structural collapse as the building's roof gives way. Russo, the facility's electrician, is in the maintenance shop when the explosions begin. He runs toward the exit as the building shakes from repeated blasts. The fifth major explosion occurs in the maintenance shop itself, where decades of dust accumulation have created explosive conditions throughout the structure. Russo is overcome by the blast as he reaches the doorway, passing away just feet from potential safety. The chain reaction of explosions lasts approximately 45 seconds from initial ignition to final blast. In that brief span, 9 men lose their lives. 3 major structures collapse or suffer catastrophic damage, and grain dust fires ignite throughout the complex. The explosions are powerful enough to register on seismographs at the University of Illinois, 70 miles away, recording as a magnitude 2.1 seismic event. Windows shatter in buildings up to a quarter mile from the facility. The sound of the blasts is heard 10 miles away, with residents initially believing they have heard thunder despite the clear sky. The Westwego Fire Department receives the first emergency call at 1:18, just seconds after the initial explosion. The caller, a secretary in the facility's administrative building which stands apart from the production structures, reports multiple explosions and visible fires. The fire department dispatches all available apparatus, recognizing immediately that they face a major industrial incident. The first engine arrives at 1:23 to find a scene of almost incomprehensible destruction. The head house has essentially ceased to exist as a recognizable structure, reduced to a skeleton of twisted steel beams and scattered debris. Grain dust fires burn in multiple locations, fed by millions of pounds of spilled grain and continuing to generate dangerous dust clouds. Fire Chief Daniel Morrison establishes command and immediately calls for mutual aid from surrounding departments. The facility's size and the nature of the emergency exceed the capacity of the local department's 30 firefighters. Morrison faces multiple challenges simultaneously: active fires burning in unstable structures, the potential for additional explosions as dust continues to be disturbed, unknown casualties, and the risk to his own personnel from structural collapse and explosion hazards. He establishes a perimeter 500 feet from the main structures and begins organizing search and rescue operations while simultaneously fighting the visible fires. The facility's surviving administrative staff provides a roster of personnel who were on duty, confirming that 9 workers were present in the production areas when the explosions occurred. None have been seen or accounted for since the blasts. Morrison organizes rescue teams, but the unstable structures and continuing fires make immediate entry impossible. Firefighters work to suppress the most dangerous fires first, using water streams to knock down flames while being acutely aware that water application to grain dust fires can sometimes worsen conditions by creating steam and disturbing additional dust deposits. The Continental Grain Company's regional management arrives at the scene by 2 o'clock, joining the emergency response coordination. Company officials provide facility plans and layouts, helping responders understand the structure's configuration and identify areas where workers might have been located. The news is grim. The head house, control room, and shipping building, All areas where workers were known to be stationed have suffered the most severe damage. The search for survivors becomes a recovery operation as the reality of the situation becomes clear. Recovery operations extend through the night and into the following day. Firefighters and emergency workers carefully search the debris, working section by section through unstable wreckage. They locate Chin's body in the ruins of the head house on the evening of December 22nd. The recovery of Hartwell and Mendoza from the collapsed control room occurs early on December 23rd. Santos and Foster are found in the main storage building later that day. Riley, Burke, and Walsh are located in the shipping building ruins on December 24th, Christmas Eve. Russo's body is recovered from the maintenance shop on December 26th. The careful, painstaking work of recovery proceeds with dignity and respect, each victim removed from the scene with full honors. The 9 workers at Continental Grain Company's Westwego facility lose their lives in the explosion and its immediate aftermath. The medical examiner determines that all 9 succumb to the blast effects and structural collapse, with the intense pressure waves and thermal conditions making survival impossible for anyone in the affected structures. The cause of death in each case reflects the violence of industrial explosions, trauma from pressure waves, thermal exposure, and structural collapse. The examiner's reports, while clinical in their language, confirm what investigators already know. The men had no chance to escape once the explosion sequence began. The immediate aftermath extends beyond the physical destruction and the recovery of the victims. Families receive notification throughout December 22nd and 23rd, each visit by company officials bringing the worst possible news just days before Christmas. The community of Westwego, already tight-knit due to its industrial focus, draws together in collective grief. The other grain facilities in town shut down operations voluntarily, both out of respect for the victims and out of sudden, sharp awareness of the risks present in their own operations. Churches hold vigil services. Local businesses close their doors on the day of the first funerals. The tragedy marks the town in ways that will persist for generations. The facility itself sustains damage estimated at $12 million in 1974 currency. 3 major structures require complete demolition and rebuilding. Grain spillage totals approximately 400,000 bushels, much of it contaminated by fire suppression water and debris. The environmental impact includes grain dust and ash that settles over a wide area, coating buildings and vehicles up to a mile from the facility. The Mississippi River receives runoff containing grain particles and fire suppression chemicals, though the dilution factor prevents significant ecological damage. The facility remains closed for investigation and will not resume operations for 8 months. The investigation into the explosion begins within hours of the blasts, with multiple agencies responding to the scene. The Illinois Department of Labor sends investigators specializing in industrial accidents. The Occupational Safety and Health Administration, a relatively new federal agency created just 3 years earlier in 1971, dispatches a team from its regional office. The National Fire Protection Association, a private organization with expertise in explosion investigations, provides technical consultation. The Continental Grain Company retains its own engineers and safety specialists to participate in the investigation. The convergence of these various entities creates a comprehensive investigation that will ultimately span 6 months and produce over 2,000 pages of findings, analysis, and recommendations. Investigators begin with scene documentation, photographing and measuring the debris field, mapping the locations where victims are found, and collecting physical evidence. The pattern of destruction provides crucial information about the explosion sequence. The most severe damage centers on the head house and elevator shaft, confirming these as the origin points of the initial blast. The secondary explosion sites show characteristic damage patterns: pressure waves radiating outward from confined spaces, structural failures consistent with rapid pressure rise, and burn patterns indicating dust cloud ignition rather than conventional fire spread. The investigation team recovers the failed bearing from the wreckage of the head house. Metallurgical analysis reveals that the bearing experienced complete lubrication failure, with metal surfaces showing scoring and heat damage consistent with prolonged operation at excessive temperatures. The bearing's temperature at the moment of failure is estimated at over 400 degrees Fahrenheit, based on metallurgical changes in the steel. Investigators determined that the bearing should have been replaced during routine maintenance, but remained in service beyond its safe operational life due to production pressures and maintenance scheduling challenges. Testing of dust samples collected from throughout the facility reveals explosive concentrations in multiple locations. The dust consists primarily of cornstarch particles measuring between 50 and 200 microns in diameter, well within the size range capable of supporting explosive combustion. Laboratory testing determines that the minimum explosive concentration for this particular dust is approximately 40 grams per cubic meter, and samples from the elevator shaft show concentrations exceeding 200 grams per cubic meter in some locations. These concentrations, when suspended in air and provided with an ignition source, create explosive mixtures with destructive power comparable to conventional explosives. Investigators examine the facility's dust collection system and find it inadequate for the operational demands placed on it. The system's design capacity assumes regular maintenance and filter replacement at intervals specified by the manufacturer, but maintenance records show that these intervals are frequently extended due to parts availability issues and competing maintenance priorities. Dust accumulation in the elevator shaft, head house, and distribution galleries far exceeds safe levels, creating the conditions necessary for the catastrophic chain reaction that claims 9 lives. The investigation also examines the facility's safety culture and management practices. Interviews with surviving employees and administrative staff reveal a pattern of production pressure overriding safety concerns. Maintenance issues are logged, but not always addressed promptly. Equipment operates beyond recommended service intervals. Dust accumulation is noted during safety inspections, but classified as a housekeeping issue rather than a critical explosion hazard. The investigation identifies systemic failures in hazard recognition, risk assessment, and safety management that contribute to the fatal outcome. Expert testimony during the investigation phase comes from grain industry specialists, explosion researchers, and mechanical engineers. Dr. Richard Morrison, a professor of chemical engineering at Purdue University, provides analysis of the dust explosion phenomenon, explaining how the seemingly innocuous dust that workers see daily can become a deadly explosive under the right conditions. His testimony emphasizes that grain dust explosions are not rare anomalies, but predictable events when dust concentrations, confinement, and ignition sources coincide. Morrison points to previous incidents in the grain industry that should have served as warnings, but were not adequately analyzed or used to drive industry-wide safety improvements. Mechanical engineer Thomas Bradford testifies about the bearing failure, explaining how the progression from normal operation to catastrophic failure could occur over hours rather than days, making it difficult for maintenance personnel to recognize the imminent danger. Bradford's analysis suggests that temperature monitoring alone is insufficient to prevent such failures, and that vibration monitoring, visual inspection protocols, and strict adherence to maintenance schedules are all necessary components of a comprehensive prevention program. The investigation's root cause analysis identifies multiple contributing factors that converge to create the fatal outcome. The primary cause is determined to be inadequate dust control and accumulation management, which creates the explosive atmospheres throughout the facility. The immediate trigger is the bearing failure and resulting sparks, but investigators emphasize that the ignition source is almost inevitable in industrial settings, and that the real failure is allowing explosive dust concentrations to develop. Contributing factors include inadequate maintenance scheduling, production pressure that discourages equipment shutdowns, insufficient hazard recognition training, and lack of comprehensive safety management systems. The investigation concludes that the 9 deaths are preventable. Proper dust control measures, adequate maintenance of the bearing assembly, and immediate shutdown when the bearing showed signs of distress would have prevented the explosion sequence. The findings emphasize that the tragedy results not from a single error or oversight, but from systemic failures in safety management that allow hazardous conditions to develop and persist until a triggering event occurs. Legal proceedings begin in early 1975 as families of the victims file wrongful death lawsuits against Continental Grain Company. The lawsuits allege negligence in maintaining safe working conditions, failure to implement adequate dust control measures, and prioritizing production over worker safety. Continental initially contests the suits but eventually enters settlement negotiations as the investigation's findings make the company's liability increasingly clear. The settlements, finalized in late 1975, total over $4 million distributed among the victims' families, though no amount of money can compensate for the lives lost or the families destroyed by the tragedy. The Occupational Safety and Health Administration issues citations against Continental Grain Company totaling $175,000, the largest OSHA penalty assessed to that date. The citations address multiple violations of general duty clauses and specific standards related to hazardous materials, machine guarding, and emergency action plans. OSHA uses the case as a catalyst for developing industry-specific standards for grain handling facilities, recognizing that existing regulations do not adequately address the unique explosion hazards present in the grain industry. The regulatory response to the Westwego explosion extends far beyond the individual citations. OSHA begins development of comprehensive grain handling facility standards that will eventually be promulgated in 1978. These standards require regular housekeeping to prevent dust accumulation, installation and maintenance of dust collection systems meeting specific performance criteria, development of written safety programs addressing explosion hazards, employee training on dust explosion risks, and implementation of hot work permit systems to control potential ignition sources. The standards also mandate that facilities develop emergency action plans and conduct regular inspections to identify and correct hazardous conditions. The National Fire Protection Association updates its standards for grain handling facilities, incorporating lessons learned from Westwego and other incidents. The new standards, published in NFPA 61 series documents, provide detailed technical requirements for dust control, explosion prevention, and explosion protection. These standards become the technical foundation for regulatory requirements and industry best practices. The grain industry, shocked by the Westwego tragedy and facing increasing regulatory scrutiny, begins investing in safety improvements across the sector. Continental Grain Company rebuilds the Westwego facility with extensive safety enhancements. The new design incorporates explosion venting systems that allow pressure relief in the event of a dust ignition, preventing the pressure buildup that caused such catastrophic damage in 1974. Dust collection systems are upgraded to industrial-grade equipment with redundant capacity and automated monitoring. The bucket elevator system includes comprehensive temperature and vibration monitoring with automatic shutdown capabilities if parameters exceed safe ranges. The facility implements a computerized maintenance management system to ensure that preventive maintenance occurs on schedule without exception. The rebuilt facility, which reopens in August 1975, becomes a showcase for grain handling safety, though this comes too late for the 9 men who lose their lives in December 1974. The long-term impact of the Westwego explosion resonates throughout the grain handling industry for decades. The incident serves as a case study in industrial safety programs, appearing in training materials, safety conferences, and engineering curricula. The technical analysis of the explosion sequence and the investigation's findings contribute to the scientific understanding of dust explosions, informing research that continues to this day. The tragedy demonstrates that organic dust, despite seeming benign in small quantities, can become as dangerous as any conventional explosive when allowed to accumulate in confined spaces. The families of the 9 victims receive ongoing support from the community and from Continental Grain Company, which establishes a trust fund to provide educational assistance for the victims' children. The company also creates a safety award in honor of the fallen workers, given annually to facilities that demonstrate excellence in safety management and hazard prevention. These gestures, while appreciated, cannot fill the void left by fathers, husbands, and sons who do not come home from work on December 22, 1974. The grain industry's safety record improves dramatically in the years following Westwego. The combination of regulatory requirements, improved technical understanding, and heightened awareness of explosion hazards drives substantial investment in safety systems and training. Dust explosions in grain facilities, while not eliminated entirely, become less frequent and less severe as the industry implements the lessons learned from Westwego and other tragedies. The number of fatalities from grain dust explosions declined significantly in the decades after 1974, a direct result of the regulatory and technical changes prompted by incidents like the one that claims 9 lives in Illinois. The memorial to the 9 workers stands at the entrance to the rebuilt Continental facility, a simple granite monument bearing the names of Robert Mendoza, James Hartwell, Paul Chun, David Santos, Michael Foster, Thomas Riley, Raymond Burke, Kevin Walsh, and Anthony Russo. The inscription reads, "In memory of those who lost their lives December 22, 1974. Their sacrifice drives our commitment to safety." Workers entering the facility pass this memorial daily, a constant reminder of the human cost of safety failures and the importance of vigilance in preventing dust accumulation and maintaining equipment properly. The technical lessons from Westwego extend beyond the grain industry. The explosion demonstrates principles applicable to any industry handling combustible dusts, including wood processing, metal fabrication, pharmaceutical manufacturing, and food processing. The understanding that fine organic or metal particles can create explosive atmospheres leads to improved safety standards across multiple sectors. The concept of housekeeping as a critical safety function rather than merely an aesthetic concern gains acceptance throughout industrial safety management. The investigation's emphasis on systemic failures rather than individual errors influences the development of safety management systems that focus on organizational culture, management commitment, and comprehensive hazard analysis. The recognition that production pressure can create unsafe conditions leads to greater emphasis on safety leadership and the importance of empowering workers to stop operations when they identify hazards. These concepts, now fundamental to industrial safety management, gain prominence partly through the analysis of incidents like Westwego, where systemic failures lead to catastrophic outcomes. The families of the victims, while grateful for the safety improvements that follow the tragedy, carry the burden of loss throughout their lives. The children who lose fathers in the explosion grow up with the knowledge that their parents' death drives changes that save other lives, a bittersweet legacy that provides some measure of meaning to senseless loss. The widows face the challenge of rebuilding their lives and raising families without their partners, supported by the community, but forever marked by the events of December 22, 1974. The Westwego explosion serves as a stark reminder that industrial work carries inherent risks and that the price of inadequate safety management is measured in human lives. The 9 men who die in the explosion are not abstract statistics, but individuals with families, dreams, and futures cut short by preventable failures. Robert Mendoza will never see his daughter graduate from college. James Hartwell will never celebrate his 20th wedding anniversary. Paul Chun will never meet his grandchildren. David Santos will never buy the house he and his wife are saving for. Michael Foster will never coach his son's Little League team. Thomas Riley will never walk down the aisle at his February wedding. Raymond Burke will never retire to the small farm he dreams of. Kevin Walsh will never take his family on the vacation to Colorado they have been planning. Anthony Russo will never finish restoring the classic car sitting in his garage. These specific, personal losses represent the true cost of the tragedy, losses that reverberate through families and communities for generations. The investigation's findings emphasize that preventing such tragedies requires constant vigilance, adequate resources for safety programs, and organizational cultures that genuinely prioritize worker safety over production metrics. The bearing that fails in the elevator head house costs approximately $300 to replace. The dust collection system upgrades that could have prevented explosive dust accumulation would have cost approximately $50,000. The total cost of the tragedy, including lives lost, facility damage, legal settlements, and regulatory penalties, exceeds $20 million. The mathematics of prevention versus consequence could not be clearer, yet the same patterns of deferred maintenance, production pressure, and inadequate hazard recognition continue to cause industrial accidents decades after Westwego. The legacy of December 22, 1974, extends beyond regulatory changes and technical improvements to encompass fundamental questions about industrial society's relationship with risk and safety. The explosion demonstrates that workers depend on their employers to provide safe working conditions and that this responsibility cannot be compromised by economic pressures or operational demands. The 9 deaths at Westwego represent a failure of this fundamental social contract, a failure that regulators, industry leaders, and society as a whole must work continuously to prevent from recurring. The current state of grain handling safety reflects the progress made since 1974, but incidents still occur, reminding the industry that eternal vigilance remains necessary. Modern grain facilities incorporate explosion suppression systems, comprehensive dust monitoring, automated equipment shutdown systems, and sophisticated maintenance management programs. Workers receive extensive training on dust explosion hazards and are empowered to stop operations when they identify unsafe conditions. These improvements, directly traceable to lessons learned from Westwego and similar incidents, have saved countless lives over the past 5 decades. The story of the Continental Grain Company explosion in Westwego, Illinois, ultimately teaches that industrial safety requires more than regulations and equipment. It demands a culture where every worker feels responsible for safety, where managers genuinely prioritize hazard prevention over production targets, and where organizations learn from incidents to prevent recurrence. The 9 men who lose their lives on December 22, 1974, die because these elements are not adequately present in their workplace. Their deaths drive changes that create safer conditions for workers who follow, but this progress comes at a terrible price. The challenge for modern industry is to maintain the commitment to safety without requiring additional tragedies to sustain motivation and resources for prevention programs. If this story about preventable tragedy and lost lives gave you insight into why safety matters in industrial settings and how dust explosion hazards must be managed, leave your like and share with others who appreciate learning from fatal accidents so that the lessons purchased with 9 lives at Westwego continue to protect workers today.